bottom. Nice. And then let me put the starting time at 12:33. Okay. So I can give somewhat of an index. I know the times I've noticed that the times I record and the times that actually then show on the video when things get spliced together are a little different. So I try to put near this timestamp, and you can kind of scan. All right, so it looks like I got 2 from 16, and we'll work on those starting with your 122, and then we'll go to 4. But hey, any 121 homework 3 question, just to see your insight. Okay, so let me, I'll maybe just write down on my paper, physics 121, homework number 3. And actually, this will give me a chance to, I've gained access to your homeworks. And let's see now if I can do that. Let's see, I need to go to Canvas. So let me start by opening Pipeline. So I'll give that just a second. Okay, and then go to Canvas. Okay. And I should have access. Oh, good. There's okay, 121. And this would be week. Let me go to week 2, right? And okay, now here are where I might need your guys' help from 121. Let's see, it looks like it says there's in red here, it says homework scaling and vector problems. Is that? Then it got discussion, reading quiz, lab report, lab quiz, homework quiz. So, anybody there in 121? What do I click on to see homework?
I don't know if it's, is it up yet? Let me see. For homework 3. Oh yeah, here, I can post the link.
Are we talking about homework 3?
I just said any homework 3, just because I moved on to 1D motion.
Okay. So I see a module that says homework 3, 1D motion. Okay, good. And then I see, I think this is kind of the reading material. So if I was doing a homework problem, what part of this module would I click on?
I posted the link in the chat.
Oh, okay. Let me jump back to Zoom here. There we go. Okay. Nice. It says loading, so that's good. And then it's script Google. So is this in Canvas and you click on something? I mean, how'd you get that link?
Yeah, there's like in Canvas they have a in the module they have like there's a little link thing that says homework 1D motion. It's right below the 3 like articles or the lecture notes or whatever.
Yeah. Okay. I see it. So I should click on that. And because the one I clicked on didn't seem to load. So I'm going to try this. It says this was opened in a new browser window. Oh no, I click here, it opens in a new browser window. Maybe I'll do that. Open in a new browser window. Okay. So it says loading. Good. Oh, good. Something popped up. Nice. Oh, and it's got a little car here. Okay. And you said anyone, you don't care which one here?
Yeah, no, I'm good with any of them just because I haven't gotten to them yet, but
okay.
I'm like basically just finishing up the chapters notes or whatever. So just any of them, just to see like your insight on like your strategies.
Okay, then I'm just going to pick the first one, and as the time goes on, we can look at some more here if you want. But all right, I'm gonna put number 1 here, and I'll leave it on my screen, and then I'll go to share my screen so you can kind of see my notepad here. I'll even write down 121 constant velocity number 1, because it's like there's 2 of them. Okay. All right. So I'm glad you say it that way, because it's good to see, people kind of work through this. This is kind of a benefit, and I think this works well, whether I do it in kind of this, I'll call it the live Zoom session, or just shooting out videos at you. It's just kind of nice to see someone start and read it, and kind of have no plan at the beginning and just kind of work their way through it. But so here it says, a car drives with a constant speed of 4.8 meters per second for a time of t. During this time, the car moves a distance of 36.2. Solve for time. All right, so one of the things that you will get or have gotten out of the reading is for constant acceleration problems, there is what I often refer to as 4 kinematic equations. This is the first one, and I think this is going to be the relevant one. But as long as I'm kind of listing them here, I'll list a second one. And sometimes I tell students that you could derive these from scratch. They're not real hard, but they're probably worth memorizing, because there are so many problems that have constant acceleration that commit these to memory. And also, I keep saying and want to remind you that only use this if you have constant acceleration. In fact, I'll pause for a moment and say, this one right here actually came from this. It actually came from the definition of acceleration is the rate at which the velocity is changing. So if you move the dt to the other side and then integrate, and this is the magical point. If you integrate this and you say that your acceleration is a constant, you can pull it out in front. So know that everything past this point is only valid for constant acceleration, because I'm sure in this homework later on, there are some problems that do not have constant acceleration. And this is just the first one. And in fact, this one's even easier. Not only is it constant, but the constant value is 0. See, they say it goes at a constant speed. So I'll address that in just a second. But keep in mind then that you will have problems that do not have a constant acceleration. And so this a must stay inside of the integral. And so they need to tell you something about the acceleration, and then it would become part of your calculus. So be on the lookout for that. It's kind of my warning for you. This one's much easier, but there'll be ones where a is not a constant. All right, now if a is a constant, then when you integrate this, and let's just say, I say from 0 to t time, and I go from 0 speed to final speed, then this just becomes t evaluated from 0 to t. This becomes v evaluated from initial to final. And when you put in these numbers, you get final minus initial. And here you get at. And if you move initial to the other side, this is what I was trying to say, that this is equation number 1. You could always start a problem and derive it, but it's such a fairly easy equation to memorize and used so often that I'm going to say that you should just memorize this. And I say that carefully because I am not a big proponent of saying memorize a bunch of equations. I, in fact, like to say, memorize very few, but there are some that is just better if you do. And in fact, I think I shot this out to you guys, or maybe I haven't completely shot it out to you guys. I need to do that. Oh, I think TJ, we were talking about this last time, that I do have a bunch of lectures online that you guys could watch. And I think in that lecture, I derived these equations and say, hey, don't memorize too many, but these two are worth it.
Yeah, sorry I didn't respond to you yet. I was gonna get back to you.
Yeah.
I'll shoot you an email later.
Yeah. Okay. Okay. So now with that in mind, let me then apply this equation. And so you need to know that, the V is the final speed, the 0 is the initial speed, and acceleration and time. Now, this equation, although useful, is really not going to help us for this problem, but I hope I'm not taking the problem too long for you. In fact, why don't I not integrate it again? But if I did the same integration, see, because velocity is distance per time, if I move the dt to the other side and basically did the same math, I would get equation number 2, where this x I put up here, and maybe I should have put a little final, and final would be the final position. X naught would be the initial position. V naught would be the initial velocity. T would be the time. A would be the acceleration. And so this is what I call the equation number 2. So like I said, I'm going to encourage you to memorize these two. In fact, you could, here's a judgment call, but if you solved number 1 for time, so it would look like this, V final minus V initial divided by A, and you put it into equation number 2, and unless you want me to do a bunch of algebra, you will get what we often call equation number 3. And this is the one that, I don't know if this one's worth memorizing. It's not too hard to memorize it. So part of me says, oh yeah, you should memorize it. It's also one that we can use a lot. So again, another part of me says, oh yeah, we should memorize it. But on the other hand, you don't ever really need equation number 3, because equation number 3 is just the combination of 1 and 2. So if you've already committed to memory 1 and 2, you can do every problem. The only advantage would be that if you do memorize number 3, you just plug the things in and finish. It's one step. Whereas if you don't memorize it, you got to come back and then solve number 1 and then put it into number 2 again. And so it becomes a 2-step process. So, that's a trade-off, right? So that's kind of what I'm saying. All right, but maybe I carried on too much. My apologies. Let's actually get to the problem. So the actual do the problem, I'm going to write down equation number 2. And I'll say it again. I can only use equation number 2 if there's a constant acceleration. So I need to read the problem. And I like to encourage students to always, when you read a problem like these one-dimensional ones, and even when you get to the two-dimensional ones, pause for a moment and ask yourself, is this a constant acceleration problem? Because you've got these 2 equations, maybe 3 equations memorized that are only valid for constant acceleration. So it says it drives at a speed, and the fact that they just gave us a number tells me it's a constant. So that means acceleration is 0. And 0 is a constant number. So whether it comes out to be a 7 or an 8 or a 3, as long as it's a constant, I can use this equation. Oh, I'm sorry, I forgot the A in here. So that's how I would first validate that I can use this equation, that I have a constant acceleration. And better than that, and this is probably why it's the first problem, is not only is it constant, but its value is 0. And so that wipes out this whole term. And of course, A means the change in acceleration. So whatever the initial speed is, which is 4.8, would also be the final speed, which would be the speed all the time. So if I fill in what I know, here's what I got. This is the final position, this is the initial position, this is the speed, and this is the time. And I'm looking for time. And it says that during the time the car moves 36.2. Now, I like to think of it this way. If I put final minus initial together and think of that as one term, that's how far it moves, right? That is the final spot minus the initial spot. Now, I suppose you could actually draw a coordinate and say, I'm going to call the initial spot 0. That means the final spot is 36.2. And that works too. So you can assign a value to each of them, or you could just, not worry about assigning a starting point and just recognize that when you are subtracting the final and the initial, what that actually means. Oh, I can use that phrase again. If we read the math here, so I like to use that phrase. This final minus initial is really how far does it travel? Okay, so this is the 36.2, no matter how you want to cut it. And I suppose with a little more accuracy, I should put in the units. So 36.2 meters for the distance, and the speed 4.8 meters per second. And so when you move it to the other side, the numbers become 36.2 divided by 4.8. The units would be meters from the distance, and then downstairs would be meters per second, and then we would be left with time. And then meters would cancel. Seconds would flip over because it's a compound fraction. So the units come out to be seconds. That's good. And then grabbing a calculator, I would just go 36.2 and divide it by 4.8 and get 7.54 seconds. And so that's kind of my thinking on this one. Thanks. Hey, TJ, you have sunshine wherever you are.
Yeah, I'm down in Pasadena.
Oh.
Is Santa Barbara pretty rainy right now?
No rain. Well, and I should clarify, I don't live in Santa Barbara. I live in Ventura. Santa Barbara is just too expensive for me, so I have a little bit of a commute. But it's pretty. I'm gonna look out the window. Yeah, during the break, I went out and stretched my legs and played fetch with my dog to get her some exercise. And I was kind of cold. It was windy and cloudy, and I go, all right, I don't want to be outside here. But then I look at you and you're outside. I'm like, hey, that's not fair.
I'm getting last minute sunshine because it's supposed to rain in like a few hours. So
okay.
Big shifts.
Okay.
Just rained here, which means it's probably heading to Santa Barbara, then Ventura, then Pasadena.
Yeah.
Where are you, Daniel?
I'm in Lompoc. It's an hour north of Santa Barbara.
Yeah, nice. Yeah, thanks, Michael. That was a good explanation. But could you go back and how did you get that acceleration is 0? Is that because it's just constant? So
yeah. Okay, so be mindful of what acceleration means. In fact, this will give me a chance to use that word again. Make sure you read the math as you're doing your physics, not just, plugging and chugging into it. So the definition of acceleration is a measurement of how the velocity is changing. So if somebody were to tell you
the velocity is not changing, it just says it's like driving with the speed of blah blah blah. Yeah. 4.8 meters per second.
Yeah.
So that means it's not changing.
Right.
Okay.
Right. Now, I suppose if you did it mathematically, you might do something like this. Take the derivative of the number 4.8. Well, the derivative of any constant is just 0.
Yeah, gotcha.
Yeah. Mhm.
Yeah.
So that's kind of the thinking there.
Yeah, there's no change in velocity, or it's just 4.8 meters per second.
All right. All right, so let me come back here. Let me go to little chat here. Okay, so I don't see any other ones from 121. So, and I'll come back to you, TJ, if you want, but why don't I've been promising Hunter for a while, we'll finally get to his. So why don't I finally get to his here? All right. So let me put here 123, number 22 at about 12:53. Oh, hey, I should ask you guys who are here kind of regularly. I noticed today I picked up my blue marker, and I, in the past, have been using my red marker. I'd always thought that the red marker stood out more. Does it really matter, or?
Could I see the difference?
Oh, sure. So if I wrote 2 pi r, 2 pi r.
Yeah, red stands out.
Okay.
Yeah,
I think actually, now that I think about it, it stands out even better when I do something like 4/2 versus 4/2. And I actually write on the line, huh?
Oh yeah, you can't really see the fraction there. And the fraction.
All right. So good. I'm gonna go back to the red one. I totally forgot. The only bad thing about the red one is it's so liquidy. It bleeds through. So when I start doing these, otherwise I get red dots on the next page, and that too is confusing. So, okay, good. All right, so let's go to back to the red marker, and then let's get started here. All right, so chapter 16, number 22 here, and I need to jump back over and read that one. Okay, so 22 here. 22 says we have a transverse traveling wave on a taunt wire, and it has an amplitude of 0.2 millimeters. So maybe I'll just write down amplitude 0.2 millimeters. And maybe I'll just, even if it's going to matter later on, write that as meters. So millimeter is times 10 to the minus 3. So there's the amplitude. Okay. And a frequency, and so here is F, 500 hertz. Okay, hertz, nice. It travels with a speed of 196 meters per second. So 196 meters per second is the speed. Write the equation in SI units. Oh, okay. Let me pause right there. SI units. Okay. So I'm glad I switched it to meters. Okay. In this form. All right. So the form that we've learned for a wave is this. The A is its amplitude. The K is what we call the angular wave number. And the omega is the angular frequency. Now, they directly gave me the A, so I don't think there's much I need to do there. Now, the K, the angular wave number, is 2 pi divided by the wavelength. Now, that means I need to get the wavelength. And I'll do that by reminding myself that wavelength times frequency is velocity. So the wavelength would be velocity divided by frequency, and those two they gave me. So this would be 196 meters per second for the speed, and 500. And let me not put hertz, let me put per second, so that I can kind of visually see that the per second is going to cancel, and I'm going to be left with a meter. Okay, so grabbing a calculator, 196 divided by 500 is a wavelength of 0.392. So now I can put that over to here, 2 pi divided by 0.392 meters. All right, so grab my calculator. There's the 2 and the pi. Let me divide that by the last answer. And I get about a 16.1. And the unit we like to call this is a per meter. It's actually a meter in the denominator. So it's kind of a weird looking unit. It's like a per second, although usually when we get a per second, then we go, hey, let's call the per second a hertz. But we don't have a special name for this. So we always just leave it as the per meter. All right, so the angular wave number is 16.0 per meter. Okay, so that's that one. Now, the negative here means it goes in the positive direction. And let me come back up here. Did they say which way this wave is supposed to traveling? A transverse wave on a taut wire with a frequency of travels with a speed of. Write the equation. Okay, so they don't deliberately say it's traveling to the right, but they do say make it with a negative sign. So it is traveling to the right. So not really part of this problem, but I would say that keep in mind that you can have a plus or a minus here, and the minus means it goes to the right, and the plus means it goes to the left. Now, the angular frequency is 2 pi times the normal frequency. So 2 pi, and the normal frequency in this case is the 500. And again, instead of writing it as a hertz, let me write it as a per second. And this would be 1,000 pi, and I'll even just throw in a clarifier, radians per second. And I guess I could even change it to a decimal, but I'm going to leave that one as a pi, see what happens. I know that I changed this pi from the angular wave number to a decimal, but that's because I had a decimal down there. But this came out to be a nice round number. Okay, so now I think I'm finally done with part A, where it says, okay, here's the equation, y equals. So I'd have the amplitude, 0.0002. Oops.
Just a quick question. I lagged out for a second. Lambda is the wavelength, right?
Yes.
Okay, cool. Thank you.
Yeah. Okay, so transferring this down into here, A is the amplitude, then I would have sine, and then K is that angular wave number, which comes from the wavelength. So that was that 16.0, so that'd be X. Then minus the omega, so that would be the 1,000 pi t, and there would be the answer to A. What is the equation? Just write the equation in SI units. And I suppose I should jump over to the solution page just to make sure. Doesn't seem tricky about that one, so I'll make sure I didn't make a mistake here. Good, we got the same thing, although they did multiply this out because pi is 3.1415. So if you multiply by 1,000, that would be 3,141.5 t. So they multiplied that out, got a decimal out of it. Oh, actually, then they rounded. They didn't do the 0.5 or the 0.1, but that's fine. And then they put that in scientific notation. Anyways, I think you'll see that those two are the same. So let me go on to page 2. I'll call it part B here. And so part B would be saying the mass per unit length of this wire is 4.1 grams per meter. Find the tension. So velocity is equal to the square root of the tension over the mass density, or put another way, when we square it, velocity squared then is tension over mass density. And then this one's asking for us to find the tension. So if you take the velocity squared and multiply by the mass density. So the velocity, let's come back here. What did I say? It was 196 meters per second. So I'll square that. And we've got another unit challenge here. We got probably to be careful with our unit because I would like tension, I think, to be in newtons. Newton has a kilogram in there. They gave us 4.10 grams per meter. I'm going to write it as kilograms per meter. Let's see for you. So I'd move it 3. And then that way, this squared would be a meter squared, canceling with that m would leave 1 meters. The seconds would be squared, and the kilogram would be there. And see, all of that is a Newton. So in order for tension to come out in newtons, I needed my mass in kilograms. All right, so now I can grab my calculator and go 196 squared and multiply by 0.0041 and get 157.5 newtons.
Dr. Young?
Yeah.
Is that for the V, is that mu or m? Like the V squared under the T?
Oh, so
Yeah, what's that symbol?
Oh, that's supposed to be a mu.
Okay. That's what I thought. I just wanted to make sure. Thank you.
Yeah. Try to be a little more careful here. Mu. I hope that's closer. Okay, so there's the tension. And B, is there a C to this one? Find this. No, so nice. Nice. That was a lot shorter than the other ones we did. How come you didn't answer that one? Ask that one first, Hunter.
They got ahead of me.
Got ahead of you, huh?
Mhm.
Okay. All right. Okay. So I hope that helped. Let me jump back over to my Zoom and see my chat, see what we got.
Yeah, thanks for that. I appreciate it.
Oh, and TJ, if you're still wondering, this was the 123 class. So I was kind of working with them. You guys have priority right now. And I took yours. I don't see another one from 121, but Hunter, I'm going to jump back. I mean, TJ, I'm going to hunt back to you. Do you want me to do a second one?
I'm down for anything. Yeah.
Down for it. All right. All right. Oh, Daniel, and then it looks like you answered him. Thanks. Oh, and TJ, you said cool. All right. All right. So you figured that out. All right. So then before we go on to number 4, I'm going to jump back to a 121 one. 121, I'll put a time of like 106. And let me not do the second one because that looked like almost the same. I don't think that'll be as helpful for you. Why don't I go down to, let's see, 1, 2, 3. Looks like the 4th one here. So let's call this physics 121. I'll call it number 4. I see they're not really labeled 1, 2, 3, 4. So I better write, it says 1D motion with velocity function. So this will be interesting to see what that means here. All right, now, TJ and the others of you in 121, I want to point out that, especially at the beginning here, this one-dimensional motion, the first question I'm going to be asking myself is this a constant acceleration problem? Because remember those 2 equations. I'm going to use them, and they even make a third one. All right. So, I don't know if it's constant acceleration yet or not, but I'm always going to keep that in the back of my mind because, as I said, we've got these equations that we can use right away, and we got to know that we can't use them if we don't have constant acceleration. Okay, so it says here, a ball rolls up a ramp, slowing and eventually rolling back down. Okay, I also like to doodle a little bit because I think it helps set the brain for getting a good physical picture of what's going on. So the part I've read so far is kind of this. It looks like it's a ball, and it says the ball rolls up the ramp. So it's rolling up the ramp. So it goes up. And I know just from my own experience that a ball rolling up the ramp would be slowing down. So this is definitely one where the speed is changing. Okay. That still hasn't answered my question about, is the acceleration a constant? I do know the acceleration is not zero like it was in the first one I showed you. Definitely know there's an acceleration. Okay, but it slows down and eventually rolls back. So in other words, it doesn't roll off the top. So maybe it comes up to here, comes to a stop, and then rolls back down. Okay. Its velocity is given by the function. Oh, okay. Now, here, they actually write.
Gave you the function?
Yeah, they actually write the function for me. I will say then that if this function is valid, that right there is telling me I have constant acceleration and I can use that equation. But in this case, it's easier. They gave it to me, so I know I can use it. Okay. Where, and then the problem lists, V naught is the 6.09 meters per second. Okay, good. And the acceleration is negative 1.95 meters per second squared, which, by the way, that right there tells me constant acceleration because, you know, they gave me a number. It's not something that has an equation that changes with time. So I would say both of these statements are telling me I have constant acceleration. This one tells me it's not only constant, but it actually tells me the value and the direction. Now, the initial speed, just to make sure you are reading your numbers carefully, notice it says the initial speed is a positive 6. So they're calling up the ramp the positive x direction. Now, I don't know if that's going to be important, but it is maybe an important note to make as I am constantly going to use this phrase, read the math. And they say initially it's going positive. And then, of course, the negative means it's pulling it down the ramp. But that makes sense. Pulling it down the ramp would slow it down on its way up and speed it up on its way back. So, okay. It makes me wish that I had drawn my ramp this way because it's a little more to the right and I'm kind of used to having things to the right be positive. So I don't know if you want to change the direction of the ramp in our discussion or leave it alone, but it is important to recognize at this point as you're reading the problem that up the ramp is the positive x-axis. That's what these positive and negatives are telling me. And of course, the other thing it's telling me is I have constant acceleration, so I can use this equation. Now, well, again, maybe I spent a little too much time just kind of reading those, but that's what goes through my head first when I read these. And then it says the ball is at the bottom of the ramp, that is x equals to 0 at time equals to 0. Okay. So the bottom of the ramp on this x-axis. Whoop, I shouldn't have wrote a grid like that. Bummer. Pay no attention to that one. But the x-axis is going up the ramp. Okay, so page 3. I'll draw my up the ramp here. But this right here is x equals to 0. And then this is the positive x-axis going up the ramp. The ball reaches its maximum position on the ramp, x equals max. Okay, so somewhere up here, it gets its maximum before it rolls back down. The ball reaches the bottom of the ramp on the way down at time t, bottom of the ramp. Solve for these two variables. Okay. So they want to know where it ultimately goes. Now, let me expand on this. I'm going to repeat what I call equation number 1.
So
But I'm
would
also going
T
to write.
ramp be just 2 times
Pardon me?
T, would time of the ramp just be 2 times the time of it going all the way up?
Yeah,
So it goes
actually,
all the
it
way
would
up
be.
and then goes all the way back down.
Yeah. So, okay, so there's a couple ways we could do that. We could prove that to ourselves. Or take it as given. I was going to do this. Maybe I'll do both. I was going to say, since I know this equation, what I call equation number 1 is valid because they gave it to me, that also means equation number 2 is valid. And so if I put x equals to 0 for the final spot and it starts at 0, and I go to solve this by putting in my initial speed of 6.09 t and my acceleration as negative 1.95, this equation would, when I solve it, gives all the moments in time when it is at position 0. And watch this. Each of these have a t in it, so I can factor it out. And this reminds me of a nice algebra problem where I have 2 factors that when I multiply them together, I get 0. And that means either the first factor is 0 or the second factor is 0. And I would say then physically what that means is one answer is when the ball is on its way up, and that would be this. So it equals position of 0 at time equals to 0 on the way up. And so this one here would be the time it is at position 0 after it comes back down. So that's why there's 2 answers here. So 6.09 equals 1.95 t over 2, and solve this for time would be 6.09 times 2. Hello. It froze on me, huh?
Yeah, it did.
Okay. Let me stop my sharing and try again. All right, so when that comes back on, you'll kind of see some math I did before I noticed it was frozen. Okay, so I'll just kind of backtrack here. But here's what I was trying to show you guys is that if you take equation number 2 and set it equal to 0, and maybe this is the long way, because I like, TJ, what you said. I'm going to do your way also, but this is what popped in my mind first is, okay, let me just put position 0 and solve for all the times when it is at 0. And so that's a quadratic equation, which means there's 2 solutions, which is perfect because on the way up and on the way down. So the first solution is pretty obvious. It's just 0, and that's on the way up. But then the other one, I'm working through the math, and I was just grabbing my calculator. when I noticed it was frozen. So 6.09 times 2, then divided by 1.95 comes out to be 6.25 seconds. So those are the 2 times that it would be at position 0. And of course, the one they are asking for is this one, the one on its way back down. So you have to kind of know by reading the math here, which is the appropriate one. But again, it's probably pretty obvious that 0 is not the one they want. They want the one coming down. Now, Hunter, you said this. You said, well, maybe another approach. And so let me do that one. Is to figure out the time it takes to get to the top and double it. All right, I'm good with that. And it almost makes the math a little bit easier because I don't have to use what I call equation 2. I can do equation 1 because one thing I do know, and I'll come back to the original drawing I drew here, as the ball goes up the ramp, when it gets to the very top, it stops before running back down. So the velocity is 0 right here. So what I could do is say, okay, using equation 1, I could put in a 0. And then really what I would be solving for is the time when the velocity is 0. So that would be the time going up the ramp. And then as you pointed out, double that to get the answer. Okay, so I'll do that. And so at 0 speed, it starts with this speed of 6.09 as an acceleration of negative 1.95 t. And so if I solve this for t, let's see, this would move over to here and become a negative 6.09. And then I would divide it by a negative 1.95. And I would get a time of 3.123 seconds to go up the ramp. So if I double that, so times 2, I get 6.25 seconds. So that works also. So not a surprise. Either approach works great. And I would say I could even think of a third one. Another one might be this. Kind of like you figured out, TJ, that it would take double the time. I could have said, well, you know what would happen is as it comes back down the hill, it's going to be picking up speed at the same rate it lost. So when it gets down to the bottom, it would be going the same speed, but in the other direction. So I could do this. I could start with equation number 1 and say that, okay, we're starting with a speed of 6.09. I want to know when it gets back. And so when does it have a speed of negative 6.09? Because negative 6.09 is, when it got back to where it started. And that would be another one, although that one doesn't pop into my head first thing. So I don't know if I would have thought about that one first, but let me give it a try and see what I get. So I get a negative 6.09 and move this over. So minus another 6.09. Divide all of that by the negative 1.95. And sure enough, I get 6.25 seconds. So all 3 approaches are equally as valid. And there is no one better than the other, I suppose. But I'd say for you, TJ, this is the best one because this is what you were thinking. You're thinking, okay, I can figure out the time to get up and then double it. Now, we're not done that. I guess that's what, half of it, because that's the time on the ramp. And then it asks for the maximum height. Be fairly easy at this point because we back here using TJ's method here, we got the time it took to get to the top right there. The 3.123. And why don't I just use that and put it into equation 2? And so, all right. This is page 4. But let me rewrite equation number 2. And so the initial position on its way up is 0. Its initial speed on the way up is 6.09. The time to go up is the 3.123 seconds. The acceleration is the negative 1.95. And then the time is the 3.123 squared. Now, I suppose I should be a little careful with the units. This would be meters per second and then multiplied by second. So this term here is going to be just meters. And this right here would be units of meters per second squared. And then the time would be in seconds, and I'd square that. So again, seconds squared meters. Okay. So each term is going to be meters. And so I can combine them together and get a final answer in meters. All right. So now I'll grab my calculator. So 6.09 times 3.123 plus a 1/2 times a negative 1.95 times a 3.123 squared equals, and it looks like it goes up about 9.5 meters before it comes back down. All right, nice. Cool. All right, well, I'm glad we worked that one in for you, you 121 guys and gals, but I guess I mean it in a non-generic way. But for you 121 people, how's that? And so let's, whoops, I keep doing that when I come back. Okay, so let's go to, how about chapter 16, number 4. That looks like the second one that's not from the 121 class. All right, and let me just kind of put some of my scratch paper in here and kind of get me started. I don't know if this is a long one or not. Number 4 sounds like it's early on, so I don't think this is going to be a long one here. But let me just write down the time. So 125. We'll do a 123 problem number 4. Okay. Good. And let me find number 4 for you guys. All right. So number 4 says, it's about waves here. These are earthquake waves, seismic waves. So it says a seismograph station receives S waves and P waves from an earthquake. Now, I know it's not really part of this class, but I can't help but kind of explain an important part of waves. If you're in a solid, so let's call the earth a rock. Now, I know it's pieces of rock, but if there's kind of a shifting or a movement, let's say I shake, it's a fault, and this part moves maybe off at an angle like that. That's really 2 motions. It's a motion that's moving towards this next molecule, and it's a motion that is perpendicular to that molecule. And it turns out then that when you bump straight into another molecule, there's a much stronger interaction than when you go perpendicular. Because when you go perpendicular, you're just kind of dragging this next molecule up. But here you're crashing into it. So when you have an initial vibration, the vibrations that compress actually travel faster than the waves that go perpendicular. So in our terminology, the longitudinal wave travels faster than the transverse wave. Seismologists call these P waves and S waves. In English, we like to say that the P stands for the primary wave. So if you're some distance away from an earthquake, you're going to feel these waves first, the longitudinal waves, because they travel faster. And hence, primary is kind of a nice description. Later on, you'll get these, what they call the secondary waves. And so S, and they're perpendicular. It's also nice because in the German word, and I don't speak German, but perpendicular in German apparently starts with an S. So it's good to remember if you know your German. And the compression or longitudinal in German is a P. Anyway, so if you know your German, you can remember it that way. But it's easier just to call it primary and secondary. For us, it doesn't really matter, but I mentioned a little bit about earthquakes. Here's what it's saying then. So if the earthquake was here and maybe deep inside the earth, so maybe this is the surface of the earth up here, then you're standing not right above the earthquake. Right above it, by the way, is called the epicenter of the earthquake. But where it actually takes place is the hypocenter. So the waves travel out. But as they get to you, the faster traveling waves, the primary waves, will get to you first, and then later on the secondary waves. So scientists have discovered that this is a good way to measure where the earthquake came from, because if one travels faster than the other, you can imagine like this pen and my finger starting at the same place. But if the pen travels a little faster, then after a moment in time, the how far apart they are is an indication of how long they've been traveling, which is an indication of where they started from. So you put your detector somewhere and you just measure the time between the P and the S wave. And it'll tell you how far away it came from. Okay, and that's what this problem is really getting at. It says the station receives the S waves and the P waves from the earthquakes, and they are 17.3 seconds apart. Assume the waves have traveled over the same path with a speed of, and here's a slower one, 4.7 kilometers per second. And then the faster one, 7.8 kilometers per second. Find the distance from the seismograph to the hypercenter of the earthquake. All right. So now that we kind of took a moment to talk about earthquakes a little bit, here's that idea. So let me just kind of say, okay, so here's the hypocenter. Here it travels out to the seismograph. Let's say that the fastest one took a time of t to get there. So I would say distance, which is velocity times time. And I don't really know the distance, but I do know the speed of the faster one. So the speed of the faster one is 7.8 kilometers per second. And that the time, so this is the time it took for the fast one, equals d. All right. Now, let me put a little divider line here on my paper and say, let's talk about the slow one here. So the slow one's going to travel the same path. And that's what they're saying here. Assume they travel the same path. That doesn't always happen. That's why sometimes you can get an initial reading on your Richter scale and then it gets readjusted when the scientists have more time to analyze it. And they just kind of assume they went the same path at first. But if they do the same path, then I've still got D. I've got velocity times time. Now, in this case, the velocity is a smaller amount. It is what, 4.5 kilometers per second. And the time is t plus 17.3. So let me just remind you, the t in my equation is the time for the fast wave to get there. And they make it very clear that the two waves arrive at different amount of time by 17.3 seconds. So what they're saying here is the time for the slower wave is the time for the fast wave plus 17.3 seconds. And they both travel a distance of d. So if we set the two equal together, we get 7.8 t on, I'll call it the left-hand side. And on the right-hand side, we get 4.5 t plus 17.3. And of course, that's one equation, and we can solve for t. Why don't I do it this way? 7.8 t equals, we'll have to do the distributive property. What is 4.5 times 17.3? And so this would be 77.85. I'll move this over to here, and I'd have 7.8 minus 4.5, and so this becomes 3.3 t equals 77.85. And then finally, you take that 77.85 and divide it by 3.3, and I get 23.6 seconds. Okay, so the time for the fast one to get to my, I was going to say Richter scale, but I guess technically it's a seismograph that is displayed on a Richter scale. Okay, is 23.6. Now I need to come back to the question because I don't know, they didn't ask for time, right? What they ask for? Oh, distance. All right, so now I can put time, and at this point, it doesn't matter whether I put it into the equation for the slow wave because it travels the same distance as the fast wave, and I'll just use the fast wave. So this would be 7.8 kilometers per second, 23.6 seconds. And so I'll just go times 7.8 and get 1.84 kilometers. And there is the distance that the seismograph is from the
Yeah,
hypocenter.
it's an easy one. I was trying to do it using all the wave stuff that we've been learning because it's in a chapter about waves, and I couldn't figure out what was going on.
Yeah, good point. I mean, this is really a mechanics problem. This would be the same as, saying something I had two people racing. One goes fast, one goes slow. And then you measure the time between the finisher, the first one and the second one. Yeah. So it really doesn't matter that they're waves. It's just two moving objects at different speeds. Yeah.
Cool. Thank you.
All right. And I suppose I should swing over here to the solutions. It doesn't seem tricky about it, so I hope I did that one right. Yeah, 184, good. Okay, and so jumping back over here to the Zoom. Let's see. I guess I'll ask you again, TJ. Do I go back to 121 again here?
I mean, I don't have any more questions, but
All right.
at least yet.
Yeah.
You haven't gotten.
I get that. Yeah, just like a lot of people, just pop in and just hang out and listen. That's all they're doing. And
Yeah, this is the only live. Oh, actually, no, that's not true. I got my computer science stuff, but only live math and physics stuff. So
yeah, oh, and I want to get some information to all of you guys. There's some tutoring options available. We should have 2 tutors. We've got 1 hired and started already, and I just need to send you the link. I'm trying to think of her days. I'm sorry, I was a little slow. We got her set up this week. The second tutor, we're trying to set her up because the tutor we did have, she got, despite the pandemic, she got some kind of study abroad program going. So she took off to Europe. So good for her, bad for us. Anyway, so I'm in the process of hiring another one. And remember, and we also have the Net Tutors. I should show you the Net Tutors. It's through your Canvas. That's available 24/7. They might be a little more out of touch with exactly what you're doing, but if you just told them the problem, I would presumably work through that and nail that one. So I need to get that information to you guys about the tutoring, but the tutoring would be live is what I'm getting at. Oh, and and another one, I got to get this written down, but the math tutoring's done a really good job because besides having math tutoring, they've kind of surveyed all their tutors, and a lot of their tutors are physics and engineering people who've gone through this program. And so they've kind of added on their resume that if anybody in 123 or 121 has a question, even though this technically is the math tutor, send them our way, and I can, and I think there's a couple there. I got to look that up, especially before we get into the harder stuff here. So maybe this weekend I can get that looked up and typed out and give you guys some options for some more live tutoring. But again, keep in mind, anytime, just shoot me a question and it's not live, but I'll work through the video kind of carefully and step by step. And I think those are helpful, right?
yeah, that's helpful. Thanks so much, Michael.
Yeah. Okay, so with that in mind, let's jump over then to whatever's next on the 123 docket. And so 123, let's see, that was 4. Let me scan down, and it looks like 56 from Hunter. All right.
I gotta get going, Michael. Have a great one.
Okay, you too. All right, peace be with you.
You too.
Okay, so, and I better write down the time, 1:41. Okay, so when I send out the video, I think people like to watch the videos so they don't have to sit here and watch the camera crash. Okay, so I'm going to put chapter 16, number 56, and then I'm going to jump over to 50, 56. Here we go. Yeah, okay, another one where things vary. We might have some calculus here. Let's see what happens here. It says a wire has a density that is tapered, so its cross-sectional area changes according to this equation. I'm going to write that down. Area is 1 times 10 to the negative, and I need to put this at 100%. Is that 10 to the minus 3 x plus 0.01 square meters. All right. Now, let me just kind of read this math for a moment. I guess it's a linear function. It would mean it has an intercept right here and a positive slope and goes up like that. And so if I was plotting area versus position, it starts with a reasonable amount of area and then gets wider. So this would be a wire that's getting more and more area, which probably means it's getting heavier and the mass density is changing. And I know the mass density is tied to velocity. And so that's the challenging part of the ones we did, which were 57 and 58. So I kind of think that's coming here. Kind of depends what they ask. Okay, so that's my start. Now I get to the question A. So question A, according to blank, the tension in the wire is T, okay, T. Derive a relationship for the speed of the wave as a function of position. Okay, so I'll say it again. The velocity of a wave is always the tension over the mass density. Now, again, maybe drawing a picture here. This, to my mind, this wire kind of looks like this. It's kind of tapering out, you know, and it's being tugged on by a tension of T both ways. But the fact that it's getting fatter means that the velocity is going to change and then decrease at the fat side here. So this is the part that changes, the mass density. The tension does not. So that's going to be just left alone. Okay, but let's talk about mass density for a moment. And so I'm going to say mu. The mass density would be something like this. It would be a little bit of mass in a little bit of length, dx. How about that? Derive a relationship as a function of position. Now, the wire, I need to go back to the beginning part, is made out of some kind of material that says density is rho. So at the beginning, it says a wire of density rho. So let me write this. Rho is mass per volume. And let me try to make a capital V here. And the reason I think that's important, and let's see if I've got a different color I can draw with. If I were to take one of these little slices here and color it in green, you know, and say that that little slice has a length of dx, its volume would be its area times its length. And so I'm kind of thinking of this, you know, kind of like, oh, what tapers? A carrot might be good. So if I had, you know, I had a carrot that tapered and I'm cutting it with a knife, chop, 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 chop. Right here, I would get kind of this coin-shaped object. Looking if I had a coin nearby. Thought I did, but anyways, I think you get the idea. This isn't a solid coin, so this isn't quite the same thing, but you know, kind of this slice here, slice. And if I want to know the volume of this, I would take its area and then I'd multiply by, well, I'd call it its height if I was holding it this way, but holding it this way, I'd call it its length. And that's what I'm trying to say here. So the volume of this little thing is its area times its length. So right here where I have density, I'm going to replace the dV, the little volume, with area times dx. And then right here, remember dm dx, so these two together is mu. And so I would say that a convenient way of writing mu is to write it as the density of whatever this material is, whatever this wire is made out of, okay, times area, and that function they gave me. So that means I know that this would be density times this function, which would be 1 times 10 to the minus 3 times x plus 0.01. All right. So that becomes real helpful because, again, here's my goal is to find, as they said, find the velocity. How'd they phrase it? Derive a relationship for the speed of the wave as a function of position. Okay. So now I have tension still in the numerator, but now I could put mass density as volume density. I guess I should call length density. So this is length density would equal volume density times area. And in fact, for those of you who went through the hard stuff of 122 and our charge densities, hopefully you remember that. We did a lot of things like charge per length versus charge per volume, and the connection between them was the area. So if you take a charge per volume, or in this case, mass per volume, and multiply by area, you will get a mass per length or charge per length. All right, but kind of a repeat for those of you who've gone through 122, and maybe a prep for those of you who are going to take 122 next fall. We can talk about the mass per length and the mass per volume, and the charge per length and the charge per volume. Anyways, I think I got it now, right? This is an equation that, given the tension of that wire, given the density of that wire, whatever it's made out of, say maybe it's made out of steel. Since most cables and strings are made out of steel. So take the density of steel and then a function of x. So there it is, and it varies with x. And if we send a wire down here, a pulse through it, and ask for the total time, those are the type of problems we did in 57 and 58, and you also are asked to do in 65. I don't think this was one of them. I don't remember this one exactly, but I don't think we have to do calculus with it. But I think I'm done, and I should probably jump over, or done with A, I should say. And I should probably jump over and check the solution of this. 56 will be far down, and see what they have. So they got the square root, good. They got the tension, they got that. They've got the, that. Oh, and let me be very careful. I should watch my units. I'm going to jump back up to this equation. They said square centimeters. So if I want this to be in meters and seconds, back here, I should have wrote down, I'll write it at the top, area would be 1 times 10 to the minus 3x plus 0.01. And then I should square the centa. So centa is 10 to the minus 2, and you square it, you get 10 to the minus 4 meters squared. So back here, I should have had a times 10 to the minus 4 if I'm dealing with meters, and I want to, and I see your author did. And so I had left it in centimeters. So I would prefer to have my tension in newtons, and because it's in newtons, I would prefer then to have my area and density in kilograms and meters. So this really needs a times 10 to the minus 4 next to it for that to work. And I see that your author has that because of the centimeters squared. to meters squared. Okay, so good. I'm glad I looked at the answer there. Okay, so B goes on to say, assuming that the wire is made out of aluminum and is under a tension of, there it is, 24 newtons. See, I knew they were going to talk about something in newtons, and I knew I needed to get this in meters. So there's the 24 newtons. Determine the speed of the wave at x equals to 10. Oh, and the origin. I skipped right over that. So it's two parts. So in other words, at the origin, x equals to 0, and at 10. Okay, so I got the equation. Let me keep the equation close by and handy. And then say, all right, let's do this. At x equals to 0, what's the velocity? Okay, so they said the tension would be the 24. And again, just watch my units, but this is 24 newtons. Okay, good. Then the density, and they say it's aluminum. Now for that, I'm pretty sure aluminum is 2.7 grams per cubic centimeter, which makes 2,700 kilograms per cubic meter. But just to make sure, let me look it up.
You actually got it. I just looked it up. It's 2.7 grams per centimeter cubed.
Thank you. All right, good. And you could probably these days, it's easier just to Google it, but it's also, of course, covered in your book. And that's, they did all the densities in chapter 14, if you remember. So if you're in the Survey book, turn to 14. And I think also in the OpenStax, they have all the densities listed in 14. They might have put it on a front cover. All right, so let me do the density. 2,700. And again, let me make sure it's in kilograms, because remember, in fact, I'll just put my units in. The unit for the tension is a Newton. And so I need to get this in kilograms and then the cubic meters. And now my density would be, and let's do the origin first. So putting in here x equals to 0, that one goes away. So it's just 0.01. And then it's the times 10 to the minus 4. And again, if you remember, that would be a unit of a square meter. That's why we had the 10 to the minus 4, so we can get it in units of square meter. And if I look at my units here for a second, and so a Newton is a kilogram meter per second squared, you will see that in the bottom down here, these 2 square meters cancel with 2 more, leaving 1 meter, which when it flips around goes with that meter, which is a meter squared. And then of course, when you take these square roots, then you just have the meter. And the kilogram down here would cancel with the kilogram. And the second that's inside of this Newton would be downstairs. It'd be a second squared, but taking the square root would be seconds. So meters per second is the final units for this, as it should be, because it's a velocity. So good, I feel comfortable about that. I should never overlook the unit analysis stuff. And, you know, if our formula is right, we can kind of confirm it with the units working out right. And so sure enough, the units work out to be meters per second, and that's what they should, because it's supposed to be equal to a velocity, and that's the units that are used to measure a velocity. Okay, good. All right, so now I can grab my calculator here. And so it looks like in the top, I have a 24. I'll divide that by 2,700. I'll divide that by 0.01. And I will divide that by, how about I just write that? Let's see, 10 to the minus 4. Would that be 0.123? 4, yeah. All right, so I'll do all that. And finally, mathematically, take the square roots, and 94.3 meters per second is what I get here. And jumping over to the author's solution, he got 94.3. Nice. Now, and I almost forgot, there's more to this. The other part of this said, find it at also x equals to 10 meters. And just as a chance to say, make sure your equations and your formulas mean something to you when you're reading this math. This is saying that the density is getting, or area is getting bigger and bigger and bigger and bigger and bigger and bigger as you go along this wire. So out at 10 meters, we've got a pretty high mass density compared to 0. And because of that, the mass density would be greater, the velocity should be lower. So I hopefully will get a number smaller than the 94 because of that. All right, and so let me put all this in again. I'll put the tension, so there's the 24 in the numerator. There is the 2700 for the density. Now I would have 1 times 10 to the minus 3 multiplied by position of 10. And I guess that makes 10 to the minus 2, and then that's a 10 to the minus 2. So this is 2 times 10 to the minus 2. And so together this is 2 times 10 to the minus 6. So let me try that here. Let me take my calculator here and go 24 divided by 2700, also divided by 2 times 10 to the negative 6. And let me take the square root of all of this. And it looks like I get a number of 66.7, and the units would be the same thing we just discussed, meters per second. So 66.7, and let's see what they get. And they got 66.7. Yay. Okay, good. Nice match.
Awesome. Yeah, I was having a hard time setting up that first part and using the density there. So
Yeah. Yeah, all of those, this 56, because it varies, anything with the variation is just harder. 56, 57, 58, and then those are the ones we did today. And I think 65 is kind of along those same ones. So these ending ones are kind of your challenging ones. All right, let's see, what's next here? All right, so that was number what, 56? Looks like there's a 26. All right, so.
Yeah, I have a question about it because I know
Uh-huh.
how to get velocity equals a square root of mass, gravity, and then length, and then divided by the mass of the string. But
Okay.
I'm not sure what to do next.
Okay, fair enough. Fair enough here. Okay, so let me actually look at this problem. Number 26. Let me actually write it down with a time stamp of 2:01. Oh, and then we'll finish this one and take our break. Looks like it's break time here. But yeah, I remember somebody asked me to read this one. A little confusing here. Okay, so and it's kind of a review of the last chapter, which to be quite honest, it's probably why I picked it. I said, oh, this is a good one. It'll kind of do our waves, but kind of reinforce it's the last chapter. But let me just read it. It says a simple pendulum consists of a ball of mass capital M hanging from a uniform string of mass little m and of length L, with little m much greater or much less than capital M. Okay, so if I was drawing a picture, I guess I'd start this way. Here's the mass M of length L, and it's got an object of capital M. And they're saying then that you can pretty much ignore the mass of the string in terms of this problem. Okay. Now they call it a pendulum. So if we were to rock it back and forth, it would have a period of 2 pi times the square root of L over G. So this is the part that I was kind of referring to, that we need to go back to last chapter. Now, if you'll notice, I spelled out the word period purposely because the symbol we used last chapter was the capital T for period. However, in this chapter, we've also been using the capital T for tension in the string. And I didn't want you to confuse that. This is period. Because
Okay.
you told me, and I'll go on to read the problem, it says, let T represent the period. Okay, so T is the period for the oscillations. Determine the speed of the transverse wave. All right, so maybe I'll split my paper in half and write over here that the velocity is the square root of the tension over the mass per length. Now again, notice I wrote it out because it's tempting to put a T up here, but I don't want to do that for this problem because you might confuse the T here for tension with the T here for period. So I'm going to do this. I'm going to use another common symbol for tension, and that's F with a small t, or a subscript of capital T. Now, for mass per length, I'm going to use the mu. I don't think you'll confuse that. But this is what you told me. You said, okay, you know this much, but you weren't real sure where to go with it. Okay, and fair enough. Okay. All right. So here's where I'll give you your first answer. So let me just do the tension. And so if I were to maybe make a little mark on the string and do a free body diagram. And so there's that little point. I would have the tension pulling up. And again, let me spell out tension. I'm not just use capital T. And then what's pulling it down is the weight. And they said that it was okay for us to ignore the weight of the string, and we just had to worry about the hanging weight. So this would be capital MG. And if it's just kind of hanging here, these have to be equal, right? The force going up equals the force going down. So I'm going to do this. I'm going to say then that the tension is just capital MG. Now the mass density, this is the mass density of the string. So I think another confusing point here could be confusing your M's. See, I was trying to be careful not to confuse tension with period because they both use a T. But I also want to be careful not to confuse capital M with little m. You see, the tension here is determined by the big mass. So I use capital M. But this under here is the mass density or the mass per length of the string. So this would be little m over L. And so that's probably the first step you're asking about here is, okay, where do I go once I do this? And so I would say that what you do, you start here, good, and that's where you started. But the first thing I do after that is to write down the equation for the tension based upon capital mass or capital M. And then the second thing is to write down the mass density, the mass per length, as what it is equal to, which would have the small m in it. Now, if I simplify this a little bit, I got the capital M, got the G, and the L can flip because it's a compound fraction, and so you flip and multiply. Okay. Now, I don't think we're quite ready to end because they specifically say, determine the speed of the transverse wave on the string of the pendulum when the pendulum is at rest, which is, by the way, that's how I said that those have to add up to 0 because, you know, it's at rest. So the acceleration has to be 0. The problem could be a little clearer, but here's kind of the default. The default is you should give an answer in terms of the variable that they give in the problem, and they give t for period. However, they also give length and capital M and lowercase m. So a case could be made that we're done. And so I'm going to put a circle around it. I won't put a box. But usually the rule is to get an answer. They don't give you numbers to plug in. So they don't give me numbers.
That could be an answer.
I think, well, I don't think it's the one they want.
Oh, okay.
But they're not clear enough. So I wouldn't, I can see how any student could stop right here.
Yeah, because I stopped there and then I saw like the solution and I was confused.
Yeah. And so I totally understand. I'd be tempted to stop here because, again, the general rule is to put the final answer in the variables that they gave you in the problem. And they gave me all of these. So I would be tempted to stop. However, they also said something about the period. So why don't I do this? Why don't I take one more step? And write what the square root of L is equal to and put it in here. And so I will just write the square root of mg over the m. And then the square root of L could be written as the period times the square root of g over 2 pi. And then if we simplify it, in kind of the general rule is to write the square roots at the end. So I'll put these first. There's the period, there's the 2 pi. And then look at this, a square root of g with a square root of g makes just a g. And so you're left with just a square root of capital M over a square root of lowercase m. So I'm betting that the author stopped here so that they could have the variable for period in the final answer and not the length. And the author should have said, find an equation for the velocity in terms of the period. Maybe they did say that. Did they say that? Let t represent the period for the pendulum. Determine the speed of the transverse wave. No. So it could be written a little cleaner. And let me check the solutions. Number 26, I think this is what they wrote. They've got the, yeah, see, they wrote it in terms of period and g and 2 pi and the square root of m. So you were on the right track, and you even actually stopped in what I would call legitimate. You know, if you had done it on a test, you know, I would have to say, well, she's right. She did it right. She stuck by the convention. I wanted this, but I just wrote a question that wasn't complete. So okay, I got to give her full credit. I got to just write a better question next time.
Yeah. Okay. Thank you.
Yeah, you bet. Yeah. All right. Hey, good, everybody. All right. Well, it looks like we've come to our break time. And we've came down to the end of the questions in the chat room. So nice balance here. All right, so let's take another break and come back. Let's see, our next session starts at 3. Yeah, so we take a break from 2 to 3 and then we assume. So I will see you guys at 3 o'clock and maybe some others too. All right, guys.
Sounds good. See you in an hour.